Let us start today's class 7, that is measurement of capacitance. We have two bridges to measure the capacitance. One is de Soto's bridge, other one is sharing bridge. Let me discuss about two bridges, that is de Soto's bridge as well as sharing bridge, one by one after the other. So de Soto's bridge. The diagram what it shows here, this is modified de Soto's bridge. This bridge is the modification of the basic de Soto's bridge. The capacitors with the dielectric losses are called imperfect capacitors. Professor Grover modified the basic de Soto bridge and obtained modified de Soto bridge, and it is represented and I have shown here. This is used for the measurement of unknown imperfect capacitor. So you are looking at the circuit diagram of the de Soto's bridge. Here, the two capacitors C1 and C2 are connected with non-inductive resistances R1 and R2. So let the loss component of the two capacitors be given by two resistances R1 and small R2. You are looking at the diagram, students. Please look at the diagram, small R1 and small R2. At balance condition, expression is given by R1, you know already, R1 plus R1. Here you can see here, R1 plus R1 plus 1 by j omega C1, that is 1 by sine j omega C1 also you can write, which is equal to this. This is the equation. So simplifying, we get C1 by C2 is equal to R2 plus R2 divided by R1 plus R1, which is equal to R4 by R3. In the modified de Soto bridge, the balance condition can be easily obtained by varying the resistances in the circuit, such as resistances R1, R2, R3, and R4. The dissipation factor D of the capacitor depends on angle del. Hence, we write, you can see here, so D1 is equal to dissipation factor of capacitor C1 and D2 is equal to dissipation factor of capacitor C2. You can write omega C1 R1 and omega C2 R2 respectively. So simplifying the above equations, we get what is D2 minus D1? D2 minus D1 is equal to omega of C1 R1 minus C2 R2. But C1 by C2 is equal to R4 by R3, or C1 is equal to C2 into R4 by R3. Substituting, we get the value of C1. Finally, we can get for D2 minus D1. You are looking at the phasor diagram of de Soto's bridge. You are seeing here, this is the phasor diagram of de Soto's bridge. You are taking I1 as a reference, I1, and this is perpendicular, I1j, 1 by j omega C1 is a perpendicular, and taking the vector, this is resultant vector, that is E. So I1 R1 will be in phase with I1 I2. Again, I1 R2 is also in phase with I1 I2. So these you can see from origin to here, that is I1 R1. From origin to here, it is I1 R2. From the origin to here, it is I2 R2. From origin to here, it is I1 R1. So similarly, you can write this perpendicular. It is I1 j omega C2, I1 j omega C1. You can see the vector which is perpendicular to I1 and I2. So the resultant will give you, see, the resultant when it is added with I1 R2, when it is added with this component, you will get EC2. Again, when I1 R1 is added with this component, you get EC1. So here, I1 R1 when added with this component, the resultant you will get E1, which is similar to E2. So E1 is equal to E2. So E1, E2 plus E3, E4. You can see from here, when you add this E3, E4 is equal to E4, E1 is equal to E2. E3, this E1 is equal to E2 at R is when this component is added with E3, E4, you get the resultant voltage E. This is how you have written the phasor diagram of de Sauter's bridge. Next, let us go to sharing bridge. You are seeing here the sharing bridge. It is one of the most widely used AC bridges for the measurement of unknown capacitors, dielectric loss, and power factor. In this figure, I have shown the sharing bridge connections. It can be used for low voltages. The CX or C1 here, what I have represented, is perfect capacitor to be measured. So R1, small r1, here it is actually the series resistance. C2 is a standard capacitor, standard air capacitor having very stable value. R3 and R4 are non-inductive resistances while C4 is variable capacitor. So from the general balance equation, we know that Z1, Z4 is equal to Z2 into Z3. From that, Z1 can be written as, you can see here, R1 plus 1 by j omega C1. Z2 can be written as 1 by j omega C2. Z3 is equal to R3. Z4 is equal to R4 divided by 1 plus j omega C4 R4. Similarly, this Z1 and Z2, whatever I have written here, that is, from solving that, equating real and imaginary terms, we landed with the equation or expression R4 is equal to R3 into C1 by C2, out of which you can find C1 because that is the capacitor to be measured. Similarly, from this expression, that is after equating the real and imaginary terms, I got C1 into R1 R4, which is equal to this. Out of this, you solve for R1. So R1 is equal to C4 R3 by C2. From this, I can calculate D1. That is, the D1 is equal to tan del. Okay. So, which is equal to omega C1 R1. So, from this loss angle del can be found, can be measured. How? For a series combination of R1 and C1, the angle between the voltage across the series combination and voltage across the capacitor C1 is called loss angle del. So, tan del is given by IR1 divided by 1 by omega C. That using that I have written this equation. So tan del is equal to omega of R3 C4 by C2 into R4 by R3 into C2, which is equal to omega C4 R4. Thus, loss angle can be measured knowing the values of omega R4 and C4. Similarly, you can also find dissipation factor D. For R1 and C1 with a series circuit, it is cotangent of the phase angle phi x. Therefore, you can, from this, you can convert this, you can express in terms of cotangent. That is D is equal to cotangent of phi x, which is equal to 1 by tan phi x. Similarly, 1 divided by the same will give you omega R1 C1, which is similarly, which is equal to omega R4 C4. Thus, one thing you keep in your mind, students, the quality factor Q is equal to X by R, which is equal to 1 by omega CR. Hence, dissipation factor is reciprocal of quality factor Q and gives the information about quality of the capacitor. Thus, if the resistance R4 is fixed, then the dial of capacitor C4 can be directly calibrated to give dissipation factor D, that is quality of the capacitor. As the term omega is present in the equation, the calibration of C4 dial holds good for only one particular frequency. The different frequency can be used, but a correction should be made to multiply the C4 dial reading by the ratio of the two frequencies. Similarly, if The resistance ratio is maintained at fixed value. The dial of C3 can be graduated in terms of direct readings of C1. Okay, so commercial sharing bridge measures the capacitors from 100 picofarad to 1 microfarad with plus or minus 2% accuracy. This bridge is widely used for testing small capacitors at low voltages with very high precision. You please keep this in your mind. So that completes here the sharing bridge. Let us discuss on limitations of low voltage sharing bridge. You can see the limitations. The calibration for the dissipation factor is useful only for one value of frequency. So in order to use it for other frequencies, a correction has to be made multiplying with the frequency ratio. One more disadvantage is the detector used is not so sensitive. One more disadvantage, the next limitation is it's difficult to obtain a balanced condition, quite difficult. Lastly, errors are present in the measurement of small capacitances using a low voltage sharing bridge. So this completes the low voltage sharing bridge and the measurement of capacitance using these or this as well as sharing bridge.